Today, we're going to cover 2.3 of your textbook, which is calculating limit using the limit law. So let's go straight to it. Suppose C is a constant, and the function f of x and g of x, they both have limit exists as x approaching to a. This one is equal to a real number a, and this equal to b. A and b are real numbers. So I use this notation, the pound sign, to stand for numbers. Okay. Now, the first law is the sum law. So if you're taking the limit of the sum of the two functions, that's equal to the sum of the two limits. Okay, so that will be equal to a plus b. Similarly, if you're taking the limit of the difference of these two functions, then it's equal to the difference of the two limits. Okay, so that's the difference law. The constant multiple law here says that if you have a constant multiple of a function, and if the limit of this function here exists, then you can bring this constant multiple in front of the limit. And that's equal to this constant times this limit of this function. In this case, is a. Okay. So if you have a constant multiple times that, you can bring it in front. The product law says that if you take the limit of the product, that's equal to the product of the limit. Okay. So that's equal to a times b. The quotient law says that if you take the limit of a quotient, then that's equal to the quotient of the limit, providing that both limit exists and this limit in the denominator is not equal to 0. Okay. Now take a look at this first example. We have this graph here. This is the graph for the function f, and this is the graph for the function g. As x approaching to -2 from both sides, okay, what is f of x approaching to? Well, as x approaching to -2 from the left side and the right side, you see f of x is approaching to 3. So this limit here is equal to 3. What about for g of x? So we go along the curve, we go along the straight line here, approaching -2 from the left and approaching -2 from the right. What happened to the y value? The y value is approaching to -1. So this is equal to -1. Now, if we try to find the limit of f of x plus 5 times g of x as x approaching to -2, what happened over here is, first, we're going to use the sum law. So we break it apart. So it's the sum of this function and this function. So we use the sum law. Okay. And then later on, for this part here, we're going to use the constant multiple law. The 5 here is a constant multiple of this function. We can bring in front of this limit here. Now we know that the limit of f of x as x approaching -2 is equal to 3. So this is 3. And the limit as x approaching to -2, g of x is approaching to -1. So this part here is -1. So 3 minus 5 here is -2. So the limit here is -2. Okay. Example 2. This is a graph for this function f, and this is a graph for this function g. We try to find the limit of this quotient f of x over g of x as x approaching to 1 from both sides. So first, let's find the limit of f of x as x approaching to 1 from both sides. So we go along the graph for f. So approaching 1 here from left and the right, we see f is approaching to 4. So that's equal to 4. What about g of x? Approaching this one here from the left side, go along the graph. We see that g of x is approaching to -2. So the left-hand limit of g of x is -2. If you approach this 1 from the right side, okay, along this graph for g, you see g is approaching to -1. So this is -1. Now you see that the left-hand limit and the right-hand limit of g at 1 is not the same. No, this two-sided limit here does not exist. So it does not exist. Now, what happened to this quotient? Well, this quotient here, because this g of x here has a break here at 1, so we can try to find this limit here by considering the left-hand limit and the right-hand limit. Okay, so the left-hand limit of this quotient, we can use the quotient law. Okay, so it's the limit of this numerator divided by the limit of this denominator. Okay, well, the limit of f of x is going to be 4, so we have a 4 up here. The limit is x approaching 1 from the left side. G of x is approaching to -2, so we have a -2 over here. So this quotient here is equal to -2. 4 divided by -2 is -2. Now, what happened to the right-hand limit? For this right-hand limit, we can take the right-hand limit of f of x, which is 4. So we get still 4 on top. The right-hand limit of g of x as x approaching 1 from the right side, it is -1. So this is -1. 4 divided by -1 is -4. Now you see that the left-hand limit of this quotient and the right-hand limit of this quotient, they don't agree. So therefore, this two-sided limit here does not exist. So does not exist over here. Okay. Now we go over more limit law. Okay. This one here is the constant law. Now, if you take the limit of a constant, for example, 5, no matter x approaching to what, this constant is not going to change. So this limit here is still 5. So limit of a constant is the constant itself. Next one, the power law. This is x to the n power. When you have x to the n power, you can just go ahead and substitute this a into this x. So that's equal to a to the n. For example, x cubed, when x approaching to 2, that's equal to 2 cubed, which is a. As you can see from the graph right here, this is for x cubed, the graph for x cubed. As x approaching to 2 here from the left and from the right, go along the graph, you see the y coordinate getting closer and closer to 8. So this limit here is 8. Now, here is the power of this function f of x. When x approaching to a, you can actually bring out this power. So limit of this power is power of this limit. Okay, so you can bring this n power outside the limit. Okay. For example, if I want to find the limit of x minus 3 to the n power, you can just take this n power outside, and you take the limit of this function as x approaching to 5. So over here, you can do a direct substitution, put a 5 into x. 5 minus 3 is 2, so that's 2 to the n power. Okay. So that's the power law. The next one here is the root law. When you take the n root of x, you can rewrite that as x to the 1 over n power. So if you take the limit of the n root of x, that's the same as the n root of the limit. Over here, when you try to find the limit of q root of x as x approaching to 2, that's equal to q root of the limit of x. The limit of x as x approaching to 2 is 2. So that's equal to q root of 2. So this next one here is the n root of this function f of x. And you try to find the limit as x approaching to a. Limit of this n root is the n root of the limit. So you can bring this n root outside the limit. So we'll have this. The n over here is an positive integer, 1, 2, 3, 4, 5, etc. Let's try to do some example to apply those limit law. For this limit over here, the first law that we want to apply will be the difference law and the sum law. So we apply the difference law and the sum law. Okay. After that, we can bring out this constant multiple in front of this limit and this constant multiple in front of this limit. Okay, so we're using the constant multiple law. Okay, now what happened to this limit here? 4 is a constant. The limit of a constant is that constant itself. So that should be equal to 4. After that, over here, this is x to the second power. So we use the power law. Then we can go ahead and substitute 5 into x. So that's equal to 5 squared. Now minus, Over here, we can also use the power law again. So substitute 5 into x right here. So that's 3 times 5. And then plus this 4 here. That's equal to 39. Okay. Now, if we go back to look at the step we have been through here, using those difference law, sum law, constant multiple law, power law, etc., right? Constant law. Well, the result is the same as you do a direct substitution into this polynomial. So we substitute 5 into x here, into this polynomial. The result should be the same as what you got over here, right? So the remark I want to make here is, if f is a polynomial, then what happens here, you can do a direct substitution to find the limit. So because we already specified that every step you just use those difference law, sum law, constant multiple law, etc., the result will be the same as you do a direct substitution. Okay. So it's okay to do a direct substitution to find the limit, providing that this function is a polynomial function. Number 2, this function over here is not a polynomial function. It is actually a polynomial divided by polynomial. That's what we call a rational function. Okay. So first, we're going to apply the quotient law, because this is the quotient of these two functions. So we're going to have the limit of the function on top divided by the limit of the function in the denominator. Notice that this is a polynomial, that's a polynomial. So we just talk about, if this is a polynomial, we can just do a direct substitution in it to find the limit. So we can do direct substitution to find the limit of this and the limit for this. So the result here, so we do direct substitution. So the result is negative 1/11. Now what happened over here is, you might notice that when we do this, when we try to find the limit for this rational function, that's the same as you substitute this negative 2 directly into the x in this rational function. Okay, and when we substitute negative 2 into this rational function, negative 2 is in the domain for this rational function. In other words, negative 2 is not going to make the denominator equal to 0. Now we have another remark. If function that we're taking limit with is a polynomial or a rational function, then we can do a direct substitution to find the limit. So we can just go ahead and substitute this number into this x and evaluate f of x. We can find the limit that's equal to the limit, okay? Providing that this a here is in the domain of this function f. Okay, now let's take a break.